In this video, we're going to talk about subtyping, another important idea in COOL and other object-oriented languages. Let's begin by taking a look at the typing rule for let with initialization. So last time we looked at the let rule but didn't have the initializer, and so let's just see how adding the initializer right here changes things. So what's going to happen here? Well, first of all, notice that the body of the rule is almost the same. So we type check E1 in an environment where X has type T0, the type it's declared to have in the let, and all the other variables have whatever types O gives them, and we get out some type T1, and that will be the type of the whole thing. So this piece right here is exactly the same as before. So what's new is this line where we type check the initializer. And so how does that work? Well, first of all, under the assumptions O, we type check E0 and we get some type T0. And now this is really an aside from the main point, but notice that we use the environment O. In particular, X, the new definition of X is not available in E0. So if E0 uses the name X, that means it uses the name of some other X that's defined outside of the let, because we didn't include this definition of X in the environment for type checking E0. All right, now, but the main point, the thing I want to point out on this slide, is that E0 here has type T0, which is exactly the same type as X. And that's a requirement of this rule. It says that E0 has to have the same type as X. And that's actually fairly weak, because there's really no problem if E0 has a type which is a subtype of T0. T0 can hold any subtype of T0, and that would be absolutely fine. But here we've limited ourselves to only allowing initializers that exactly match the type of X. So we can do better if we introduce the subtyping relation on classes. And the most obvious form of subtyping is that if X is a class and it inherits directly from Y, meaning there's a line in the code that says X inherits from Y, then X should be a subtype of Y. And furthermore, this relationship is transitive. So if X is a subtype of Y and Y is a subtype of Z, then X is a subtype of Z. And finally, as you might expect, it's also reflexive. So every class is a subtype of itself. And using subtyping, we can write out a better version of the let rule with initialization. So once again, the part of the rule that deals with the body of the let is exactly the same as before. So let's not look at that. And now what we're going to do is we're going to type check E0 and we get some type T0 out. And then T0 now is only required to be a subtype of T. So this line here is another hypothesis, and it just says that T0 has to be a subtype of T. And what is T? Well, T is now the type that X is declared to be. So this allows E0 to have a type that's different from the type of X. And the only issue here is that more programs will type check with this rule than the previous one. The previous rule we had was certainly correct. Any program that compiled with that rule would run correctly. But this is a more permissive and still correct rule. More programs will compile and type check correctly using this rule. Subtyping shows up in a number of places in the COOL type system. Here's the rule for assignment, which is in many ways similar to the rule for let. So how does an assignment work? Well, on the left-hand side is a variable. On the right-hand side is an expression. We're going to evaluate the expression and assign whatever value we get back to the variable on the left-hand side. And so how is this type checked? Well, first of all, we have to look up the type of X in the environment, and we discover it has some type T0. And then we type check E1 in the same environment, so the set of variables here is not changing. And so we type check E1 environment O, and we get some type T1. And now what has to be true for this assignment to be correct? Well, it has to be possible for X to hold a value of type T1. So X's type T0 has to be a supertype, has to be bigger than the type of T1. So if this constraint is satisfied, then the assignment is correct. Another example that uses subtyping is the rule for attribute initialization, which except for the scope of identifiers is very, very similar to the rule for normal assignment. So recall what a class looks like. You can declare a class in COOL, and it has at the top level some set of attributes and methods. And what does an attribute definition look like? Well, it looks like one of these things. It's a variable declared to have some type, and it can have an initializer on the right-hand side. And so in what environment then is this initializer type checked? Well, it's type checked in this special environment O sub c, which just consists of the types of all the attributes that are declared in class C. So this means we have to make a pass over the class definition, pull out all the attribute definitions, all the names of the variables and their types, build an environment that records all that information, and then we can type check the initializers, because remember, the initializer for an attribute can refer to any of the attributes of the class. So let's take a look at how this works. First, we look up the type of x in the environment, that's some type t0. Now we type check E1 in the same environment, that's some type T1, and then just as with assignment, T1 needs to be a subset or a subtype of the type T0. Now we come to another interesting example, how we type check an if-then-else. And the important thing about if-then-else is that when we're doing type checking, we don't know which branch is going to be taken. We don't know whether the program is going to execute E1 or E2, and in general, actually, this if statement may, or this if expression may execute multiple times during a run of the program, and sometimes it may execute E1, and other times it may execute E2. And so what that means is that the resulting type of an if-then-else is either the type of E1 or the type of E2, and we don't know at compile time which one it's going to be. So the best we can do is to say the type of the entire if-then-else is the smallest supertype larger than the type of either E1 or E2. The need to compute an upper bound over two or more types comes up often enough that we're going to give the operation a special name. We'll call it the lub, or least upper bound, of x and y. And the least upper bound of x and y is going to be z if z is an upper bound, so meaning it's bigger than both x and y. And also if it is the least among all possible upper bounds. So what this line here says is that there is some other z prime that's bigger than x and y, well then z has to be smaller than z prime. So z is the least, it is the smallest of all the possible upper bounds of x and y. And in COOL and in most object-oriented languages, the least upper bound of two types is just their least common ancestor in the inheritance tree. So typically, the inheritance tree is rooted at object or some similarly named class that includes all the possible classes of the program, and then there's some kind of a hierarchy, which is a tree that descends from object. And if I want to find the least upper bound of two types, say this type and this type, I just have to walk back through the tree until I find their least common ancestor. And so in this case, if I pick these two types out of my tree, this would be the least upper bound of those two types. Now we can give a type checking rule for if-then-else. So the first thing to notice about if-then-else expressions is that they do not affect the environment. And if-then-else neither introduces nor removes any variables from the environment, so all the sub-expressions are typed in the same environment as the entire expression. Now the predicate of the if-then-else E0, well, that should have type bool, because that's our decision whether we're going to take the true branch or the false branch. But then the two branches can have different types. E1 just has to have some type T1, and E2 just has to have some type T2. So notice again what this is saying. This is just saying that E1 and E2 do have to type check. They have to be type correct, but we don't care what the type is. The type can be anything. And then the type of the entire expression is just going to be the least upper bound of T1 and T2, because that's going to be the best estimate we can give to the final type of the expression, given that the true branch might return T1, something of type T1, and the false branch might return something of type T2. The rule for case expressions is the most complex one we've seen so far, but really it's just a glorified if-then-else, and it's relatively easy to understand if we just pull it apart. So let's begin by reminding ourselves of what case does. First of all, it looks at E0, it evaluates E0, and then it looks at the runtime type of E0. So it takes the dynamic class of E0, and then it looks at the first branch. And what is it going to do? It's going to compare the type of E0 at runtime to the type T1. And if T1 is a supertype of the runtime type of E0, and in fact it is the smallest of all the possible branches, it's the smallest supertype of all the possible branches, then it's going to pick this branch, it's going to bind x1 to the value, it's going to give it the type T1, so it's going to bind x1 to the value of E0, it's going to retype it as type T1, and then it's going to evaluate E1. So you can see in what sense it's a glorified if-then-else. We're just picking the best matching branch, the one whose type, declared type, most closely matches the runtime type of E0, and then we're going to execute that branch with the variable that's named in that branch bound to the type of E0. So let's see how the typing works out. So first we type check E0 and we get some type T0. And now what's going to happen? Well, if we select the branch, the first branch, well, then we're going to take the environment and we're going to extend it with the new variable x1, which is going to have type T1. And so we only take this branch, remember, if a runtime type of E0 matches T1 most closely among all the branches. But if we do take it, then we're going to execute E1 in this environment, and we'll get back something of some type T1 prime. And similarly for all the other branches, until finally the last branch, which is exactly the same as the first one, just with the letter N replacing the number 1. And so since we don't know which branch is going to match at runtime, it could be any of the branches that actually executes, and therefore the type of the entire expression is just going to be the least upper bound over all of the types of the various branches. And here I've just extended least upper bound from a binary operation to an n-ary operation. That should be clear enough. We're just going to take the least upper bound over all of these types.